In this video, we're now going to demonstrate the essence of the inverse square nature of the universal law of gravitation. So consider two identical systems, two identical masses, but in the first situation, there's some distance r apart, and in the second situation, their distance has been doubled to 2r, okay? So they initially start here, and then they get doubled over here. And what I want to do is compare the size of the gravitational force between these two systems. And again, the only thing that's changing is the distance between them. The masses are going to stay the same, okay? So you can consider maybe two planets, a planet and a sun, or two bowling balls, whatever the case may be, as long as you keep the mass of m1 constant in both cases and the mass of m2 constant in both cases. And they don't necessarily have to be the same, you just have to use the same two objects, all right? So, from the last video, we saw that the universal law of gravitation can be written as g times m1 times m2 divided by the distance between them squared. And that is given by this situation right here. So that's how I would write the force law down. That's how I would calculate the gravitational force between these two objects in this situation. But if I double their distance, so the new distance between their centers is twice the original, then I would write down the force law like this: g times m1 times m2 divided by 2 times r, and that entire quantity now gets squared. You square the entire distance between the two objects. So how do these two compare? Right? So if I explicitly solve this equation, I get this. Right? I get that value. And now, to kind of get a sense of how these two forces compare, let's take the ratio of these two forces. So let's take the ratio of force 1 to force 2. Okay? So if I look at force 1, I have g m1 m2 over r squared. And I'm going to divide that by g m1 m2 divided by 4 r squared. And so, this is the big dividing line here. And you can work out the mathematics yourself. I'll do it very quickly. But at the end of the day, my masses are all going to cancel out. And my r in these two cases are now the same. This r is the same as this r. I'm just multiplying it by 2 here, so this distance r and this distance r are the same, so those cancel out. And I'm left with a fraction over a fraction, and what this boils down to, and I'll leave it to you to prove this to yourself, but what it boils down to is this number 4 right here. What this is telling you is that the force in the original case is 4 times greater than the force in the second case. So, in the first case, our objects were some distance r apart. We double that distance to 2r, and the force in the original case is 4 times greater. So what this is saying is, if I double the distance, then the force goes down by a factor of 4. If I were to halve the distance, then the force would go up by a factor of 4. If I were to halve the distance, if this were 1/2 r squared, then the ratio of f2 to f1 would be 4 times, indicating that this would be 4 times greater. Okay? And that's what the essence of the square law means. If I double the distance, the force goes down by a factor of 4. If I triple the distance, the force goes down by a factor of 9. 3 squared is 9. If I quadruple the distance, the force goes down by a factor of 16. And likewise, if I cut the distance, my original distance, by a third, then the force goes up by 9. And if I cut the distance by 1/4, then the force will go up by 16. Okay? So that is what we mean by the inverse square law. If I double the distance, then the force goes down by 4 because 4 is 2 squared. if I triple the distance, the force goes down by a factor of 9 because 9 is 3 squared. Okay, that's what we mean by the inverse square law, and that's how this law works, and we'll see a couple other laws down the road also work this way as well.